So because the slope of a line measures the ratio of its rise to its run, what it's really doing is it's measuring the direction that a line goes in. And because the slope measures the direction, we can use it as a marker to determine whether two lines are parallel to one another, in other words, they go in the same direction, or whether two lines are perpendicular to one another, meaning that they meet at a right angle, a 90-degree angle. So in this example, we start out with a line which we're given, and we need to find an equation for another line which is either parallel to it in part A, or perpendicular to it in part B, and which passes through a specified point. So what's our strategy going to be? Well, each of these questions is asking us to find an equation for a line which passes through a given point and which has a given direction. And so we again have the option of either using a point-slope form of an equation, which I prefer, or using the slope-intercept, y equals mx plus b formalism. The only difference in this problem is that we're not being given the slope sort of spoon-fed. Instead, we have to figure out what we need the slope to be based on the requirement either that the lines are parallel to one another, and two parallel lines will have the same slope because they go in the same direction, or perpendicular to one another. And two lines which are perpendicular have slopes which are opposite reciprocal to one another. In other words, we take the reciprocal, we flip a fraction upside down, and we also trade positive for negative. And so these two pieces of information are the only things that make this a new problem. That if you see the word parallel, you know the slopes of the two lines are going to be the same. If you see perpendicular, you know their slopes are going to be opposite reciprocals. So the strategy involves, first of all, looking at the line that we're given in the problem and figuring out what its slope is. If we can't figure out the slope of the original line, then we have nothing to compare it to make the slopes of our new lines. Once we figure the slope of the original line, we're either going to keep that slope, if I want a line which is parallel to it, or we're going to flip it upside down and change its sign, opposite reciprocal, if we want a line which is perpendicular to it. Then we'll take that slope and plunk it into either our point slope or our slope-intercept forms of equation for a linear function. Again, because I prefer it, we'll write a point-slope equation, using the new slope that we decided as well as the point that we're given in the problem. Alright, so let's get started by finding the slope of the original line that we're given in the problem, y equals 3/2 x. Well, how do we find the slope of a line given an equation that looks like this? Because the y is already solved for, we can see it as a y equals mx plus b situation, right? Where the m, the coefficient of the x variable on the right-hand side, is 3/2, and the b, since nothing was written there as an additive constant term, we can think of that as being 0. And in y equals mx plus b, the slope is the value of m, that coefficient which is attached to the x. So the slope of our original line is 3/2. That's going to give us our starting point for the slopes of the lines that we're looking for in parts A and B. So let's suppose that I want to find an equation of a line in part A which is parallel to the line that we started with. Well, parallel lines have identical slopes. So the slope of the line that we need to write an equation for in part A is the same as the slope of the original. In other words, the slope of this line had better be 3/2. So the way I like to see this is let's just forget about the original statement of the problem and just cross out the parallel business and just imagine that the problem is asking find an equation of the line that has a slope of 3/2 and which passes through this given point. So now we're back to a situation where we have a point and we have a slope and we want to write an equation for the line. We know how to do that. Let's use the point-slope form of an equation for a linear relationship. Y minus y1 is equal to m times x minus x1, where m is the slope that we want, and x1 and y1 are the coordinates of the point that we want. Well, the slope we want was 3/2. And the point, 9, 6, we'll put the 9 in the x box and the 6 in the y box. And there is an equation for this line. Of course, if we want to simplify this further to solve it for y, we can do that. It's always a good practice to do. So we'll distribute the 3/2 on the right-hand side to get 3/2 x minus 3/2 times 9, which is 3/2 times 9 over 1, which multiplying straight across gives us 27 over 2. And then to finish solving for y, we just need to add 6 to both sides to get y equals 3/2 x minus 27/2 plus 6, which if I want to add those fractions together, I'll rewrite 6 as 12/2, and then negative 27 plus 12 is going to give me negative 15. So an equation for the line that is parallel to our original and which passes through the point 9, 6 is y equals 3 halves x minus 15 halves. Again, most important thing about this first part of the problem was that we knew the slope needed to be 3 halves because we wanted this line to be parallel to the original line, and parallel lines have identical slopes. Okay, what about the perpendicular part? For part B, we want an equation of a line which is perpendicular to our original line and which passes through the point 9, 6. Well, perpendicular lines have slopes which are opposite reciprocal to one another. In other words, we take the reciprocal, we flip a fraction upside down, and we also change the sign, negative to positive or vice versa. So since our original line has a slope of 3 halves, a line which is perpendicular to that original is going to have a slope which we get by flipping upside down that fraction and then also changing its sign. So 3 halves turns into 2/3 when we flip it upside down, and then we also add a negative sign out in front of it to change the sign. In other words, a line which is perpendicular to our original is going to have a slope of negative 2/3. And that allows us again to just rewrite this problem, to see it as asking to find an equation of the line that has a slope of negative 2/3 and which passes through the point 9, 6. And again, we know how to do that if we use point slope. Y minus y1 is equal to m times x minus x1. M, the slope now, is negative 2/3. The point, 9, 6, happens to be the same point that we asked for in part A. So you notice these two equations that we got, the point-slope equations, are very similar in part A and part B. The only difference is that here in part B, the slope that we got was the opposite reciprocal of the slope of the original line, rather than the same thing as the slope of the original line when we were looking for a parallel. Now we'll just finish by solving this equation for y, distributing the negative 2/3 on the right-hand side to get negative 2/3 x plus negative 2/3 times negative 9, which is positive 6, and then adding 6 to both sides gives us the equation y equals negative 2/3 x plus 12. So finding equations of lines which are parallel or perpendicular to a given line is no different than just finding an equation of a line if we know the slope and if we know a point. Using point-slope form is the easiest way to do it. The only extra layer of question that this adds on is you have to figure out what slope you need. If you're looking for a line which is parallel to the original, you want to keep the same slope as the original. So you find the slope of the original and you keep it. That was our first example where the slope was 3 halves. If instead you want a perpendicular to the original line, then take the original slope, flip it upside down, and change its sign. Take the opposite reciprocal, which in this example turned the original slope of 3 halves into a new slope negative 2/3. But once we've found the slope that we want, based on whether we want parallel or perpendicular, the rest of this problem is identical to the previous problems, where we just need to find an equation of a line with a known point and a known slope. Plugging that point and slope into the point-slope form of an equation is, for me at least, the easiest way to get it done. And in each of these examples, once we've solved for y, we then get an equation which is in slope-intercept form at the end of the day.